I'm Mark Kavanaugh for Cavi Coaches, and today I'm going to coach you up on types of collisions using momentum and energy. In this video, we're going to be talking about collision types, and the two types of collisions we're going to talk about are inelastic and elastic collisions. Now, Newton's third law governs all collisions in terms of the third law, where forces come in pairs during a collision that are equal in value and opposite in direction. So an example of a collision type where the Newton's third law governs is a bat hitting a ball. So we know that when a bat hits a ball, that the force that the bat exerts on the ball is equal and opposite to the force the ball exerts on the bat. So here are the different collision types. We have an elastic collision. And what an elastic collision is that momentum is conserved and kinetic energy is also conserved. And you'll see that this is the difference in our types of collisions is what goes on with energy because momentum is conserved in all collisions. An example of an elastic collision would be that something that's hard and the objects have no deformation, such as a billiard ball. So when the billiard balls collide, a cue ball hitting the eight ball, the cue ball and eight ball do not compress at all because the surface of the sphere of the ball is incredibly hard so that it does not collide and deform. The other type of collision, as we mentioned, is an inelastic collision. And here's the difference is that still momentum is conserved because momentum is conserved in all collision types, but it's the kinetic energy that defines the type of collision, and kinetic energy is not conserved in an inelastic collision. So in this case, objects have deformation. So an example is a car accident. So when your cars collide in an accident, the car is designed to crumble to dissipate as much energy as it can, so to protect the driver as much as it can. So that is the deformation causing it to be an inelastic collision. A specific type of inelastic collision is a perfectly inelastic collision. And what a perfectly inelastic collision is it's still the same as a inelastic collision, but in this case, the objects collide and stick together. So there's still momentum conserved. There's kinetic energy is not conserved. In fact, this is the maximum amount of kinetic energy that is dissipated is when an inelastic collision occurs and objects collide and stick together. So how do we prove if a collision is inelastic or elastic? So let's go through some steps and explain how we would do this. So we're going to use a momentum bar chart to show that the momentum is conserved, and we're going to find the velocity or mass, whatever is missing from a final situation or initial situation before and after the collision. Then we're going to use the kinetic energy equation. Kinetic energy is 1/2 mv squared to calculate the total kinetic energy before and after the collision. Then we're going to compare those values. If they're equal, it's an elastic collision. If the initial is greater than the final, then it's an inelastic collision. And you're going to see that there is no situation where we can have a collision where the overall energy increases. So these are the only two situations that we're going to look at. The only way kinetic energy would increase overall is if we had an outside object working on the system and transferring energy in. So here's our example problem. We have the cue ball that has a mass of 0.17 kilograms, and it strikes the eight ball, has the same mass straight on, and it comes to a stop. The eight ball then moves toward the pocket in the same direction the cue ball was moving before. And the question we want to ask is this an elastic or inelastic collision? So let's go through our steps. First, let's draw a momentum bar chart. So as the cue ball approaches the eight ball, we know it has momentum. So let's draw a bar that represents the cue ball, and we'll just qualitatively represent this with a total height of 4 lines. Then the eight ball moves away, and we know that it has to have the same momentum, and the cue ball stops, so it has no momentum. So we know that the eight ball is going to have the same amount of momentum that the cue ball had to start with. So then we write our conservation equation that the momentum of the cue ball is equal to the momentum of the eight ball. So we substitute our equation for momentum, mass of each times the velocity. We know that the masses are going to be the same, so that cancels out. And we see that the velocity of the cue ball is going to be equal to the velocity of the eight ball. Now we can use the kinetic energy equation, and since they have the same mass and the same velocity, we know that kinetic energy is conserved in this situation. So if kinetic energy is conserved, we know that this situation is an elastic collision because the energy before is equal to the energy after the collision in terms of kinetic energy. And we know the momentum is always conserved. So here's our second example. We have a pickup truck that rear ends a car and they move off both in the same direction, but they do not stick together. The masses and velocities are given, and we want to know if this is an elastic or inelastic collision. So what we don't know is how fast was the car moving after the collision. We know the pickup truck's values, but we don't know the car. So let's draw a momentum bar chart. So the truck approaches the car, so we have a momentum to begin with. And we know since they both move in the same direction, we're going to have a positive value for both of them as they move off together. But the truck is going to slow down. Newton's third law, the truck exerts a force on the car exerts a force equal and opposite on the truck. So the truck slows down and the car speeds up, showing the momentum in this situation. Now, after we have our momentum for each of the objects, we're going to write our conservation equation. The initial truck's momentum equals the final truck's momentum plus the car's final momentum. Then we can go ahead and we can substitute in the values for the momentums, or the equation for the momentum, mass times velocity, representing green with the truck and blue with the car. And we know the values of all things except the final velocity of the car. So because we're looking for the final velocity of the car, we're going to rearrange this equation by subtracting the truck's final momentum. Then we're going to divide both sides by the mass of the car, and that's going to give us the final velocity of the car. Then we can substitute in the values for our masses and velocities for the truck and the mass of the car. Then we can do our calculations and find that the velocity of the car final is 11.3 meters per second. Now we have to answer the question, is this an elastic collision or an inelastic collision? So what we're going to do now is we're going to calculate the kinetic energy in the initial situation. So the initial kinetic energy is going to be the mass of the truck times the velocity of the truck initial squared and half of that, and we get a total value of 170,000 joules of energy for the pickup truck before the collision. Now in the final situation, we have two things moving, so we have to calculate two kinetic energies and then add them together. So we can substitute the values in for each of the car and the truck, knowing that the car's velocity is 11.3 meters per second, and we get 42,400 joules for the truck and 95,767.5 joules for the car. And if we add those together, we get 138,267.5 joules. And now we're going to compare the initial and final, and we can see that the initial situation has more than the final situation. So if the initial situation has more than the final, then we know that that is going to be an inelastic collision. So the situation can never occur where we have an increase of energy unless there's an outside force working on it. So we know that it's either going to be the same, which is an elastic collision, or there's going to be a decrease in kinetic energy, which is an inelastic collision. This is an introduction to the two types of collisions. I hope this was helpful, and I hope you have a great day and an even better tomorrow.
If you found this video helpful, click the like button down below and subscribe to my channel, Cavi Coaches, and follow me on Instagram and Twitter @CaviCoaches.